Chapter 3, Atoms and Ionic Bonds. First, we have to define what a compound is. A compound occurs when any two different elements come together and form a bond. Now, the bond can be ionic, which we're going to discuss in this chapter, or it can be molecular, which we'll discuss in the next chapter. So, compound is any two elements that have come together to form something new. So, water, hydrogen and oxygen, ammonia, nitrogen and hydrogen, glucose, carbons, hydrogens, and oxygens. So these are all compounds. Keep in mind, oxygen, O2, is diatomic, and that is not considered a compound because it is the same element bonded effectively to itself. So what type of reactions can form ionic compounds? Well, first of all, we have to have a metal and a non-metal coming together. In this flask here, we have some sodium in the presence of chlorine gas, and this is how sodium chloride, or table salt, is formed. Here is a strip of magnesium, which is being burned, and this is forming magnesium oxide. So how does ionic bonding occur? We have to have what's called a transfer of electrons, which means something has to give up an electron and something has to accept it. Because of this electron transfer, what we end up with is the thing that gave away its electron is positive. The thing that accepted the electron is negative. So now we have positives and negatives, and they will attract each other. That is what is known as our electrostatic forces. So the force that occurs between opposite charges coming close together. Down here, for example, we have lithium with its one electron that it can give up. And when it gives up its one electron, we'll see that it becomes like a noble gas in its electronic configuration, which means that it's more stable. So it gave up its electron, it became positively charged. Fluorine, which has 7 electrons, can accept this electron to now become negatively charged. So I have lithium that lost the electron to fluorine, which took it. Now we have a positive lithium ion, a negative fluoride ion, and now we can form lithium fluoride, which is shown over here, a white powdery substance. So ways that we can determine, or I should say define, different terms in our ion category here. First of all, an ion is simply something that has a charge. Okay? Have to have a charge. When you are a cation, you are positively charged, which means this little T here we can think of as a plus symbol. So cations are positively charged. Anions must be negatively charged. So how do I remember that? A negative N ion. N is for negative. Negative, positive. Monoatomic. Hopefully we know mono means one or singular. So one atom that has a charge. You can either be positive or negative. Poly means more than one. So this is a group of atoms that are bonded together and have a charge on the overall molecule. So we see polyatomic molecules, polyatomic ions. If we look down at our periodic table, once again, we'll see how the PTOE is really our BFF. Group 1 becomes +1. Group 2 becomes +2. Why? Lost an electron, lost 2 electrons. When they do this, they become like their nearest noble gas. So lithium loses an electron to become like helium. It does not become helium. It is still a lithium ion, or it's a lithium atom. It just doesn't have the same number of electrons that it started with. Now it has the same number of electrons as helium. So group 1 is +1, group 2 is +2. Notice here in the middle we have some different charges on our transition metals. 2s and 3s, 1s and 2s. Here, mercury does really strange things. We actually have a diatomic mercury with a 2+. I will give you a list of ions that you actually need to remember. Very few things I ask you to memorize. This happens to be one of them. So transition metals do weird things. But if we look here, if we know we can start with chromium and go all the way over to nickel, they're either +2 or +3, so we have 5 elements in a row that have the same possibility for their charges, and 2 + 3 is 5. So there's one little way to kind of cheat your way through remembering what your charges are. Here in my group 11 or 1B, everything at least has a +1 charge. And here in group 12 or 2B, everything has at least a +2 charge. Now, back to main group elements. Group 3, metals, well, aluminum, is a +3. We would see the other metals follow the same trend. Group 4, if you're a non-metal like carbon, you become a -4. Versus if you are a metal like tin or lead, then you are positively charged. Metals are always going to be, well, I should say almost always going to be your cations, positively charged. So metals are all positively charged. Non-metals are usually negatively charged. So the N for non-metal is the N for negative is the N for anion. Fair enough. So group 5, now we don't have a -5 charge. Instead, what we have is a -3 charge. Why? Because nitrogen, which starts with 5 electrons, it's easiest for it to accept 3 electrons. If I count over 1, 2, 3, I'm like a noble gas. Group 6 starts with 6 electrons. So count over 1, 2, 2 electrons accepted becomes like a noble gas. All of the halogens here in group 7 all become -1 most of the time because they accept 1 electron to become like a noble gas, right? The noble gases are like the cool kids in the block. They're the most stable. Everybody wants to be like them. So if we go +1, +2, +3. We hit kind of the middle here. We're either -4 or +4. Notice tin and lead also can transition. Then we start counting down. -3, -2, -1, 0. Noble gases do not ever take a charge because they're not ever trying to give up or get any electrons. They're already stable. Excuse me. So once more, cations, positively charged, almost always metals. Anions, negatively charged, non-metals. How did I become a cation? I lost an electron. How did I become an anion? I gained an electron. So when we have ionic bonding occur, we have what's called a lattice structure, which means that we have this repeating unit or these repeating units of positively charged ions and negatively charged ions. So it's this 3D crystalline structure that we see here, a repeating pattern of our cations and anions. The energy which holds all of these ions together is called the lattice energy, and we will actually be able to calculate that in a later slide using the Born-Haber cycle. So here's our lattice structure. This is one of the reasons why we see salt as a little tiny cube, because it is a crystal and it will form and then it will get to be unstable and it will shear off at some point to start forming the new crystal. How do we name our ionic compounds? So we have to be able to communicate and not just run around saying, hey, I have some H2SO4, I need some C6H12O6. It doesn't make sense to just say elemental symbols. So we need to be able to name so that we can read labels on bottles and also communicate with others what compounds we're talking about. When we name ionic compounds, your cation will always come first. Generally speaking, then that means our metal. Our metal shows up first. If we look at our periodic table, metals show up first. If I read my periodic table like a book, metals on the left, non-metals on the right. We know my metals become positive. So positives come before negatives. The anion is second. That's our non-metal, generally speaking. And if we just have one of them, we drop the ending and give it an IDE ending. What do I mean? Hydrogen, hydride, oxygen, oxide, sulfur, sulfide, phosphorus, phosphide, etc. And you'll get a list with the names and the charges of all the elements that I'm expecting you to know. So when we are writing out our ionic compounds, we follow what's called the crisscross method, and I'll show you that in the next slide. And the crisscross method allows us to figure out how many cations and how many anions do we need for this particular compound, because ionic compounds always have to have a charge of 0. The positive charges have to cancel out the negative charges. Now, when we're naming transition metals, we have to be able to indicate whether something is a +2 or a +3 charge. The old school way was to use OUS ending for a +2 and an IC ending for a +3, or +2, +4. So the smaller charge would always take an OUS ending. This comes from having to know the Latin names. For example, lead 2 would be plumbus, because the Latin name for lead was plumbum, versus lead 4, which is plumbic. Or I could have ferrous versus ferric, argentus, aurus, auric. Okay, so you have to know the Latin names. Do we all know our Latin names of our elements? Probably not. So we use the new school, which is simply using Roman numerals. I would say lead, parentheses, and a Roman numeral 2. Or lead, parentheses, Roman numeral 4. Tells me what the oxidation number is. That charge tells me the charge based on what the Roman numeral is. So here's this crisscross method. How do I figure out my formula of an ionic compound? I'm looking at the charges, and then I'm simply bringing down the charges crisscross from where I started. Notice I'm not taking the actual charge, so I'm not ever putting minuses or pluses down here. A little verbiage here. When we find the number at the top, it's what we call a superscript. When we find a number at the bottom, we call it a subscript. So our superscripts become our subscripts. And these numbers down here represent how many of each atom we have in this compound. So what this is really telling me is that aluminum is +3, oxygen is a -2. How many of each of these atoms do I need in order for them to cancel out their charges? Basically, this is allowing me to say 2 times a +3 is +6. 3 times a -2 is a -6. +6 minus 6 equals 0. So we have to know our charges. And remember, some of these charges are easy because we just look at our periodic table and we look at our group number. Some of them we have to memorize. But this crisscross method always works. You don't have to think about it. You have to have your correct charge and simply crisscross it down. Bring the number down without the charge. So our charges on our cations become our number of atoms that we need for our anion, and vice versa. So here, if I look up potassium and I look up bromine on the periodic table, potassium is a group 1 metal, +1. Bromine is a -1 halogen. So +1 -1, I only needed 1 and 1. When we have 1s as subscripts, we do not put those on there. They're just known. Zinc, iodide. Zinc is a +2. Iodide is a -1. I took my 2, I pulled it down. I took my 1, I pulled it down. I showed you aluminum oxide down here. Here, this is called calcium phosphate, PO4. That happens to be a polyatomic anion. This will be something that's on a list that you will simply have to memorize the name and the charge and what it looks like. Now, if I know nothing else, I know that this number had to be up here to start with, and this number had to be up here to start with. So if I don't know my charges off the top of my head, I can look at my subscripts sometimes and they will tell me. Calcium was a +2. Phosphate is a -3. Now, why do I have these parentheses here? Well, this tells me that I need 2 of this entire group in order to cancel out the charges on calcium. Calcium's a +2 because it's a group 2 metal. 2 times 3 + 6. Phosphate, I pull that number up here, -3. I have 2 of them. 2 times -3 is -6, and we've canceled out. So anytime you have a polyatomic and you need more than one of them, you're always going to have to use your parentheses. And we will work these out on the worksheets and in the book. Ah, yes, here I'm showing calcium the 2 coming down, phosphate with the 3 coming down. So we don't care about the charges when we're bringing the numbers down because subscripts do not have negatives and positives. This tells me how many number of atoms do I need, or how many number of groups do I need in this compound in order for it to be charged 0. It has to be neutral. Crisscross method. Don't complicate it, folks. So at the end of last chapter, we looked at atomic radius as one of the periodic trends. Now we're also going to look at ionization energy and electron affinity to hopefully help to understand why we see ionic compounds forming. Now these trends are trends. They are not definites. They follow a certain pattern and mostly for our main group elements. Both of these things, ionization energy and electron affinity, come from that concept of effective nuclear charge. How tightly are my electrons being held onto, and how much do I want to get some more electrons? And it all comes to how do I become the most stable that I can possibly become. For example, down here, I have 2 sodium atoms that are going to lose electrons. Why? Group 1 metal. I have chlorine, which needs to be split apart, and each of the chlorines are going to accept 1 electron. Why? Because it's a group 7 nonmetal, and to be like their nearest noble gas neighbor, they get 1 electron. And now I've got these positives and negatives coming together to form sodium chloride. So once again, why is it, though, that sodium gives up the electron? Why is it that chlorine accepts the electron? I can't just say, oh, it's group 1. Group 1 helps me to remember that it's going to be a +1, and group 7, but why is this happening? So we're going to look at the why. For example, I'm looking here, and this goes back to why would an atom want to lose an electron? Well, my group 1 metal, my group 2 metal, my group 3 metal, if I lose 1 or 2 or 3 electrons, I can become like my nearest noble gas. Losing electrons allows me to become positive and have a more stable electron configuration. Now, when I put these in brackets, this means that I am abbreviating neon's electronic configuration, which means 1s2, 2s2, 2p6. So that's neon, and I can look and I can do the same thing for argon. I can also look at what is happening with some nonmetals. Hydrogen can accept an electron to become like helium. Fluorine, look, in the outermost energy level, 2 + 5 is 7 electrons. If it accepts 1 electron, now it becomes like neon. Oxygen, 6 electrons outermost orbital, accepts 2 electrons to become like neon. So our main group elements are either trying to lose or gain electrons in a way to become like the noble gases. Electron configuration only. We are not looking at actually changing nitrogen into neon. We cannot do that unless we do a nuclear reaction, remember? So atoms gain electrons. What atoms gain electrons? Non-metal atoms tend to gain electrons. So one more time here, just to clarify and solidify in our minds what our charges are when we look at our periodic table. We go up, 1, 2, 3, we're positive, and then our group 4 does different things. Oops, sorry about that. Group 4 does different things. -4 at the top, +4 is at the bottom, and we count back down. -3, -2, -1, and remember, these are 0. So what other electron configurations can we look at? Cations, remember, are metals. When they are a transition metal, what is happening? We're always going to remove our electrons from our s orbitals first, and this is because it is the energy orbital, it is the electron orbital that is farthest away from the nucleus. So these electrons are being held onto the least tight. So we remove our electrons from our s orbital, and then we go in and start to remove our electrons from our d orbital. So s orbitals first, d orbital second. And if you forget, if you look at your transition metal and whatever row it's in, if you go back to the beginning of the row, you will always see that the s orbital gets filled before the d orbital. So looking at iron, iron goes from a 0 charge to a +2 charge. Lost its 4s electrons, so we wouldn't write that down. Has 6 electrons left in its d. If it loses another electron, we end up with 3d5, and this is very stable. It's very stable to have half-filled d orbitals. It's one of those anomalies that we'll see. Notice that with our transition metals, we do not just end up with a bracket of a noble gas, because our noble gases don't have any extra leftover d electrons. So you will always have the noble gas in brackets and then some amount of d electrons when we're representing transition metal electronic configurations. Over here, manganese, how does it become +2? It loses its 2s electrons to become like argon with an extra 3d5 electron configuration. Cations and anions. So when we are forming a cation versus when we are forming an anion, the cation, lithium, becomes smaller. It is always smaller than the atom from which it was formed. Fluorine becomes bigger when it accepts an electron. So why is this? The remaining electrons that are left over feel a higher effective nuclear charge, so the atom shrinks. Versus when I'm gaining electrons here, first of all, I need to have more space because I have more things. Second, the effective nuclear charge goes down. Third, because electrons are negatively charged, they are going to repel each other and want to spread out farther away from each other. So cations, lithium to lithium plus, are shrinking because the remaining electrons are being held onto tighter. And if we think about electrons like dollars, lithium starts out with 3, it loses 1, so hey, it's going to hold on to those last 2 electrons pretty tight. Fluorine's getting an electron, so it's going to spread out. It's gaining stuff, so it's going to get bigger, and those electrons repel each other, meaning they need to take up more space. As well as the effective nuclear charge going down, so it cannot hold on to those outer electrons as tightly as before. So here's a trend of looking at what happens with our ions in terms of ionic size. We still see that we get bigger as we go down a group. We still see that we get smaller as we go across our row. Notice, though, that our anions are significantly bigger than our respective cations because our anions are getting bigger versus our cations, which get smaller. Now, this is just a trend. Certain elements do different things, but over here we're shrinking, over here we're getting bigger. Another picture to represent this trend, lithium through cesium, so group 1 alkali metals. What's happening? We notice that our size is going down, but as we move down the group, we notice that our size increases. When we look at our halogens, once again, we are seeing that here we've accepted our electrons to be up here. So we notice that our anions are bigger, and as we go down the group, we still see that the anions get bigger as we go down the halogen group or down the alkali metal group. So ionization energy. What is ionization energy? It's the amount of energy that has to be put in to take an electron away from an atom. So the energy is put in to remove an electron. Ionization energies are always positive because the energy has to be provided. So generically, we're representing some element X that is becoming positive because it lost an electron. So this I1 is the ionization energy to remove the first electron. We can remove the second electron by starting with our X plus. Take off the second electron, here it is. Now we have a positive 2 charge, second ionization energy. And we can keep going and keep removing electrons until we get to whatever charge it is that we're looking for. How is it becoming the most stable? Group 1, group 2, group 3, right? They are becoming like the noble gases. It's a stepwise process. We cannot just take 3 electrons off at the same time. We have to remove the first one, then the second one, then the third one, etc. And what we see is that as we go up in successive ionization energies, and these are for the same atom, is that your third ionization energy will always be much larger than your first. So they continue to get bigger. Why? Because these atoms continue to shrink the more electrons that are removed because the effective nuclear charge is going up. I'm remaining constant in my number of protons, so I have this positively charged center, but I'm slowly picking off electrons. The more electrons I pick away, the more dollars I'm losing. Those remaining dollars or those remaining electrons are going to get held onto even tighter, which means more energy has to be put in to remove them. Yeah, if I have $3 and you've already taken $2 away from me, hey, I'm going to fight tooth and nail to keep that last dollar. What if I want a candy bar? So here's my trend. I can look hydrogen to helium. I'm going across the row. Lithium to neon across the row. Sodium to argon across the row. So what is my trend? My ionization energies increase as I move from left to right. Why? Because I know my effective nuclear charge increases as I move from left to right. I also know that my size decreases as I move left to right. So neon is holding onto its electrons much more tightly than what lithium is. I can also look at going down a group. So here I have my alkali metals. Noticing that the ionization energy, and this is first ionization energies, tends to get smaller as I go from top to bottom. Why? Lithium has 3 electrons. Cesium has 55 electrons. Losing 1 electron out of 3 versus losing 1 electron out of 55. Much easier to take that 1 electron away here. Why? Because it's much further away from the nucleus. How far? N equals 1, N equals 2, N equals 2, N equals 3, N equals 4, N equals 5, N equals 6. Cesium's electron is being removed from the 6th energy level. Lithium's electron is being removed from the 2nd energy level. Think about the distance. How far away is this electron from the nucleus versus this? Higher effective nuclear charge, lower effective nuclear charge. So the trend, ionization energy gets bigger as you go from left to right, and it gets smaller as you go from top to bottom. So if ionization energy is what we have to put in to take an electron away, electron affinity can be thought of as the amount of energy that's given off when an atom accepts an electron. So this is affinity, means how much do you like something? So how much am I loving on my electrons here? How much do I need an electron to be happy? This energy, like I say, tends to be given off, so we look at it as a negative value. Once again, generic element X is now accepting an electron to become negatively charged. For example, fluorine and oxygen. Sometimes I just want to point out here that electron affinities can be represented as a positive value. But what we really want to do is just pay attention to the magnitude here. This energy actually truly is given off. It's just the way in which the experimentation is done and they're measuring it as to how they're reporting those values. But what we can take away from this is when fluorine accepts an electron, a lot of energy is given off in that process. When oxygen accepts an electron, not as much energy is given off. Why? Because oxygen here with a -1 charge isn't quite stable yet. It would really like to get that second electron. So we would see that there's another electron affinity energy for the O-. So how is that going to accept an electron? So electron affinity is kind of the opposite of our ionization energies. Electron affinities are normally associated with having large values for our nonmetals, right? And very small values for our metals, because metals don't want electrons. Metals want to give away their electrons to become more stable. So this is how we can see the combination of ionization energy and electron affinity coming together to form these different ionic compounds. One is giving the electron away, one is accepting. So variation of electron affinity. Once again, what are we looking at? We're looking at trends. Notice helium, and then actually this is beryllium and nitrogen. So we see some anomalies here with having energies of 0. Why would an atom have an energy of 0, electron affinity of 0? That is because those subshells, whatever shell it may be, is already full. So it doesn't want any more electrons. We know helium is a noble gas, so of course it doesn't want any electrons. But beryllium is a group 2 metal. So beryllium is a 1s2, 2s2. That's the electron configuration. It doesn't have anywhere to put any more electrons, so it doesn't want any electrons. It says, hey, I'm cool. If anything, I would just like to give away these other 2 electrons to then become like helium. So all of our noble gases and our group 2 metals tend to have electron affinities of 0. They do not want to accept electrons. Now, who wants to accept electrons? Look at these guys. All of our halogens. This should hopefully make sense because these are group 7 nonmetals. To get to 8, they accept 1 electron, which means they become stable. They become like their nearest noble gas. So high electron affinities for our halogens. Then we see, okay, group 6 nonmetals, right, that take on the -2 charge. They're next in line of, hey, they really want these electrons. And then we continue to go down the more electrons that you need in order to be stable. So as far as trends go, we see electron affinity get bigger as we go from left to right. Or sorry, I should start down here. Left to right. As we go down our group, we notice that our electron affinities tend to get smaller. Not a big derivation, though, oftentimes. What is the octet rule? The octet rule stands for the fact that 8 is great. 8 what? 8 electrons. If I have 8 electrons in my outermost shell, i.e. if I have ns2 np6, where n is whatever principal quantum number I need it to be, then I am stable because I'm like a noble gas, with the exception being helium, where helium only has 2 electrons. So all main group elements are trying to achieve that noble gas electron configuration by either losing electrons if you're a metal or gaining a certain number of electrons if you are a non-metal. So once again, let's be like the noble gases. So the last part of this in terms of ionic compounds is looking at calculating lattice energies in the Born-Haber cycle. And what this has to do is we have to look at getting our elements into the correct form, which means they need to react as gases. And in terms of our nonmetals, if they are diatomic, which in this instance chlorine is, there's a little 2 here, which means I have 2 chlorine atoms bonded together. I'm going to need to split those apart. Once I split these apart, once I make this a gas, then I'm going to have to do my electron business of taking an electron away and giving it to chlorine. And that's exactly what happens. There's no willy-nilly transfer of electrons where somebody's giving away more electrons than somebody else can accept. So here, this energy is called the energy of sublimation because I'm going from a solid to a gas. 1/2 here means that I'm only taking half of those chlorine, so I only need 1 chlorine atom. So basically what I'm putting in here is enough energy to break apart these 2 Cl atoms that are bonded together. Take half that energy. Sodium becoming sodium plus. What is this? This is an ionization energy. Chlorine accepting an electron is the electron affinity. So these are the energy values that are associated with forming sodium chloride. If I add all of these up, then I end up with what the lattice energy is for sodium chloride. All right, so on to looking at some of your basic chemistry that occurs with our main group elements. Hydrogen. Hydrogen is really in a class all by itself. It's normally listed with the group 1 metals, but we know it's not a metal. It's the most abundant element in the universe, and it goes both ways. So it can form a +1 cation when it bonds up with other nonmetals, and it can form a -1 anion when it bonds with metals. So hydrogen either likes to give its electron away, or it can accept an electron. So down here we have an example, calcium hydride. Recall ionic compound formation here. Calcium has a +2 charge. So the 2 came down here. Hydrogen, -1 charge. The 1 came down here. What happens? When we have hydrides, they tend to react with water, producing a base, calcium hydroxide, and hydrogen as a gas. Now, OH happens to be one of those polyatomic ions that you're going to have to memorize. And the charge on the OH is a -1. So, group 1A, the alkali metals, have very low ionization energy. They're never found in nature in their pure elemental state, which means that you never find sodium by itself. Sodium has to be bonded to something else in a compound. And these metals react vigorously with water and react vigorously with oxygen to form metal oxides. So here I have sodium, potassium, cesium, showing what's happening when I have these pure metals reacting with water. And these metals are actually very soft. You can cut them with a knife. They're shiny, and they always have to be kept in oil because of how reactive they are. And like I said, when we take these metals, we react them, we form bases. So we form a basic solution when we're doing this, if we have a big bucket of water. Group 2. So group 2 elements will react with water, but not as vigorously. Sometimes they won't react with water. Some need really hot water. Some need really cold water. Some have to have an acid in order to produce hydrogen gas. But it's the same, it's the same principle in terms of these metals will react and then they will form a base. So barium hydroxide. Group 3, so we start to get into some metalloids, boron, and we have aluminum, which aluminum will react with oxygen to form aluminum oxide. Aluminum almost always forms a +3 cation. And the other metals lower in the periodic table, not the metalloids, but lower in the periodic table there, end up with +1 and +3 charges. Group 4 and group 5. So now we're moving into the more non-metal side of our periodic table. Carbon can exist in a couple different ways. They're called allotropes, right? We have graphite, which we write with. We have diamond, which we can cut with or wear pretty rings. And then we also have the Buckminster ball. Carbon tends to form -4 oxidation states, but depends. It can change. Tin and lead will react with acid to produce hydrogen as a gas. So recall our metalloids here, right? They do different things. Sometimes they can behave more like a metal. Sometimes they can behave more like a non-metal. Silicon is mostly used in semiconductors and doping. Group 5. So nonmetals are nitrogen and phosphorus. Notice nitrogen is diatomic. So it always exists in this form in nature in terms of, well, I should say not always, but it can exist in its elemental state, as well as carbon and silicon and germanium. So it's group 1 group 1 metals will never exist alone. Group 2 metals can exist alone. So you can have magnesium all by itself. All right, so metalloids, arsenic and antimony, and then we have the metal bismuth. Nitrogen forms lots of oxides, and specifically N2O5, which is called dinitrogen pentoxide, which we'll learn about in the next chapter, will react with water to form nitric acid. Phosphorus is a white powder kind of crystalline structure, and it can react with oxygen to form two different compounds. And one of those compounds, I believe it's P4O10, will react with water, and then we can get phosphoric acid. These are acids, indication, there's an H in the front, and we will go over that in a later chapter. Arsenic, antimony, and bismuth all have much more complicated 3D crystalline structures. Group 6 elements, so nonmetals, oxygen, sulfur, selenium. Oxygen is diatomic. This is how it exists in nature. Sulfur, generally a yellow substance, and it smells really bad. So here we have 8. This is what this means. There's 8 sulfur atoms in an actual sulfur, in the sulfur structure. So this is elemental sulfur, and this is elemental selenium. Our metalloids, tellurium and polonium. Polonium is actually radioactive, so we don't study that a whole lot. And more complicated crystalline structure here. Now, sulfur reacts readily with oxygen in the atmosphere, which is why coal can be such a problematic thing, because there's a lot of sulfur in coal. And then what happens is we end up with sulfur dioxide, sulfur trioxide. This is sulfuric acid. Hydrosulfuric acid, and basically these can all react with water then to actually form sulfuric acid, which is acid rain. So whereas our metals would react with water to form a base, now we have our nonmetals reacting with water to form acids. Group 7 elements, so our halogens, they're all diatomic, which means F2, Cl2, Br2, I2. But they do not exist in elemental form in nature. This is good, right? Chlorine gas would kill us all if that's how it existed. So it's always bonded with something else. They tend to form ionic salts. A salt simply just means I'm going to join with a metal. I'm going to be the anion, I'm going to form a cation, and we're going to form a salt. They also form molecular compounds with each other, and they will react with hydrogen to form hydrogen halides, which basically then is an acid. Hydroiodic acid, hydrochloric acid, hydrofluoric acid, hydrobromic acid. So once again, nonmetals react with water to form acids. They also react with hydrogen to form acids. And last but not least, we have our group 8 elements. They're all monoatomic. They are found in nature by themselves. They were considered inert, which means that they did not think that these elements reacted. But then xenon and krypton were used to form compounds, most notably with fluorine, because fluorine is so reactive. Fluorine is so vigorous when it comes to wanting an electron. It will force bonding on these noble gases. There's no major commercial use except for, helium. We fill balloons and we can suck it in to make our voices sound different. All right, what happens when we compare the group 1A and the group 1B elements? So group 1A, so each of these have or tend to form a positive 1 charge. However, your 1B metals are much less reactive than your 1A metals. And this is because when we're in the B group, we're in those transition metals. So we have all those electrons in the d orbitals kind of interfering with valence electron chemistry there. So your 1B metals, copper, silver, and gold, are called your coinage metals. And we know that copper, silver, and gold, they're rare, but you can dig in the earth and find them, and they are found by themselves. They're very stable. You will not find sodium buried in the earth anywhere. It's not stable. So your 1B metals, your transition metals, are much, much more stable, meaning they are not as reactive as what your group 1 metals are. And the same holds true for group 2A metals and group 2B metals. And that, my friends, ends this chapter material. So we will look at writing ionic compounds, getting our correct formula structures for ionic compounds. You guys will memorize your ions, your polyatomic anions and cations, and take a look at your generalizations, your trends, and what we see with ionic radii, ionization energy, electron affinity. And then we also like to take a look at what are some common reactions that our groups will do, right? Group 1 metals. What is a common reaction that we see with them versus a group 7 non-metal? What are the common reactions that we see with those? Alrighty, guys, keep studying.